Okay, so welcome back. The second lecture. The first one is on YouTube, and I emailed it to everybody. So check it out if you missed the first one. But anyway, we're going to continue in the direction of that last lecture by now talking about groups. So last time we talked about sets and how to distinguish them or distinguish between them in a meaningful way. And what we wanted was we wanted sets which differ by a relabeling to somehow be equivalent to each other. And the way to accomplish that was through the use of an equivalence relation. The one that we used declared all sets connected by a bijection to be equivalent. So bijection, for example, our working example was this map that sent 1, 2, 3 to ABC. Well, you could define a lot of different ones, but for example, the one that sends 1 to B, 2 to A, and 3 to C. So the point is that everything on the left gets mapped to something, and only one thing. And no two things on the left get mapped to the same thing on the right. And everything on the right is hit by this map. So there is something on the left which maps to it, right? And when you have all these properties, then what you have is a bijection. So finally, it turned out that a complete invariant in the setting of finite sets was the order of the set, right? So in order to figure out whether two sets were equivalent, so if I wanted to know if A was what I was calling isomorphic to B, then all I had to do was check to see if the order of A was equal to the order of B. So this is for finite sets. If they are, then the two sets are equivalent. And if they're not, then they're different. So this was not true for infinite sets, but we didn't go into any detail there. Okay, so this is all well and good, but it maybe isn't so interesting. The idea of a map was very useful in our study of sets. So in an attempt to kind of remedy our boredom here, let's watch what happens when we give our set G. Let's take a set G. And let's give it a friend in the form of a binary map. So I'll call it star. Binary map goes from the product of a set with itself to itself. So maybe I should explain what this symbol means. This G cross G is the set of all pairs of elements, G1, G2, such that G1 and G2 are both elements of G. So the idea is give me two elements of G and I'll give you another one. Okay, so the first thing we should do is define what exactly a group is. So a group is a set G equipped with a binary map, which we'll call star. Some people call this a binary operation. That's fine too. Satisfying three properties. First is called associativity. So the way I'm going to, whoops, that should be K. Fix that. The way I'm going to write the action of the binary map is by writing the map in between the two things it's acting on, right? So instead of writing star of G1, G2 equals, whatever, G3, I'm going to write G1 star G2, just like we do with addition, multiplication, and so on. So associativity says that it doesn't matter in which order we apply this map. This is for all G, H, and K in my group G. Just in case some of us haven't seen the symbol, this is for all. And the second is we need the existence of an identity element. So we need that there exists an element E in the group. Doesn't really matter what we call it, but let's use E, such that E acting on G, sorry, the action of the map on E with G just gives us G. And in fact, it works the same both ways. So if you're multiplying two things, then the identity would be one, right? One times anything, just nothing. If you're summing integers, for example, then the identity is zero, right? Zero plus whatever is the other thing. And then the last thing you need is the existence of inverses. We need that for every G in the group. There is another element, which we call G to the minus one, or G inverse, such that G star G inverse is the identity. And the same for the other direction. So this is associativity. This is the existence of an identity. And this is invertibility. Okay, so first thing I want to notice is that we're not requiring here that this thing is commutative. Right? So we don't require G star H to be equal to H star G. So multiplication of the reals is commutative. Addition of integers is commutative. Something that's not commutative is matrix multiplication, right? And there are many other circumstances. But when this is true, when this is true for all G, H, and the group G, we say that the group is abelian. Let me point out an abusive notation that's common. So technically, the entirety of a group is a set with the binary map here, right? So if I just write G by itself, what I mean is the set, but there's an abusive notation where we just denote this whole thing by, the label for the set. So in the future, it should be clear from the context whether something's a group or not. So I won't write this whole thing, this tuple anymore. I'll just write this whole thing as G. So it might seem like we've chosen the conditions, 1 through 3 here kind of arbitrarily. But what we'll see is that these are really the conditions needed to describe symmetry in a physical setting. So still, though, there are more general structures, and there's this nice plot of, well, maybe I'll just write something out really quick. So if you just take a set and equip it with a binary map or binary operation, what that's called is a magma. And then what you can do is you can add divisibility So you don't have an identity yet, so you can't add invertibility yet. But you can add divisibility, which just means that if you have two elements A and B, then you can find elements X and Y such that A star X is B, and that's equal to Y star A. That's called divisibility. And when you have that property, what you have is a quasi-group. On the other hand, instead of that, you could add property 2, which is the existence of an identity. Then what you have is a unital magma. You could also give the magma associativity. Then what you have is a semigroup. So this is divisibility. This is property 2. This is property 1. And then the quasi-group, if you give it an identity, you get a loop. You get an inverse semigroup by going from the quasi-group and giving it associativity, or going from the semigroup and giving it divisibility. And there's the idea of a monoid, which you get from a semigroup, giving it an identity, and well, from the unital magma, you could get there as well. Okay, so well, I've gotten this far. Maybe I'll just give you the rest of the graph. Give it inverses, you get a loop from unital magma, and then from here, everything goes to a group.
What about rings?
So rings are groups with extra structure. So you would continue down this way. Yeah. So there's a third map in that case. But this is associativity, this is identity, and this is invertibility. So there is a plethora of algebraic structures that we could study, right? And so the question becomes, why do we want to study groups? Well, because, well, from an algebraic perspective, you would study all these things, right? But groups turn out to have applications in so many different fields, but particularly in physics. So groups describe symmetries in nature. So that's the reason we want to study those. Yes, Roy.
Oh, so I see for the loop, it requires divisibility in the second property or the second property in the first property. So how are those equivalent somehow? I mean, obviously, but how are they equivalent, I guess?
So if you have divisibility and then you also have an identity element, well, that's equivalent to having an identity and invertibility. Right? So inverses are unique in this setting. Okay. All right, so let's continue. Any other questions before I continue on?
Wait, could you put the map back up for a second?
Sure.
I am. Oh, sorry, I just misread the
So this map is, I think, listed in the Wikipedia article on semigroups, maybe. Yeah, it's one of these structures, I think, on the right, either semigroups or monoids. Okay, so first thing we should do when we define something is give an example. So here's one that we're all familiar with, which is the integers under addition. So the operation here is addition, which is something we're all used to. We know that addition is associative, right? If I take three numbers, n, m, and k, let's say, it doesn't matter if I add them n plus m first or m plus k first, right? We can do it in whatever order we like. It has an identity element. The identity is 0. Right? Why is that the identity? Because 0 plus n is n, which is n plus 0. And it has an inverse. Inverses always exist. So given an n, the inverse is minus n. Right? That takes us to the identity element. So that's a group. Right? There's nothing more to it. More interesting example is if you draw a triangle. Let's label the vertices here, 1, 2, 3. Well, the triangle is invariant under a rotation by 120 degrees. Right? If I rotate this thing 120 degrees, it looks exactly the same. Right? The numbers are displaced, but the numbers aren't a part of this construction. Right? The triangle itself looks exactly the same. So the triangle is invariant under rotations of 120 degrees. So what if I rotate it twice? Then that's 240 degrees and it still looks the same. If I do it a third time, that's 360 degrees and it still looks the same. And now my numbers are also in the same order, right? So rotating 360 degrees is the same as doing nothing. So what we can do is we can write a set. Let's call the set, well, for reasons to be seen later, we're going to call it C3. And the set's going to consist of a rotation, which we'll call R. This is a rotation by 120 degrees. And then R squared is just the composition of two rotations. So that's a rotation of 240 degrees. And then R cubed is a rotation of 360 degrees, which is, of course, the same thing as doing nothing. So that's our identity element. We'll call that E. E is the same thing as R cubed. Okay. Well, there's two ways to think of the operation here. We can think of it pictorially, the rotations of the triangle. We can also think of this as a multiplication, right? Multiplication of R with itself a number of times, right? With the caveat that R cubed is always equal to the identity. So let's check that this thing is a group. So we have that the binary operation is either multiplication with the understanding that R cubed is the identity, or just the rotations in the picture here, whichever you prefer. So for associativity, well, obviously this thing's associative because no matter what I take from this set, it's always R times itself a number of times, right? It doesn't matter if I do R times R squared or R times R squared times R, or R times R times R, whatever. These are all the same. We're going to get associativity because everything is just the power of R. So what's the identity? Well, it's this do nothing element, which is equivalent to rotating by 360 degrees. Right? And then the inverses, well, we can just list them all out. So the inverse of doing nothing is doing nothing. How do I get to the identity from the identity? Well, I just multiply by the identity again. The inverse of R is R squared because R times R squared is R cubed, which is the identity. And then the inverse of R squared is just R, because again, R squared times R is R cubed, which is the identity. So indeed, this thing is a group. So it's a group called a cyclic group of order 3. It appears in several other ways, including integers modulo 3. But this is a nice picture because it allows us to move to the next step, the next example. So notice that our triangle here is also left invariant by a flip along one of the following axes. Pretend I drew those straight. It's also invariant by flipping across one of these axes. It looks exactly the same. So if we include these flips in our group, we get an even bigger group called the dihedral group of order 6. So the elements of the dihedral group, which I'll call D6, are the identity, the rotation squared, so that's the cyclic group, and then a flip. I haven't specified which axis to flip about. It turns out it doesn't really matter, right? Whichever one you choose, you can get the other flips as an element in this set. So I'm not going to look for an example. That would take a little bit of time, but the flip about this axis can be written as some rotation multiplied by a flip about this axis, for example. Right. So everything else, all the other flips are actually in this set. Right? They're just hidden. So we don't need to include them. Okay. So this group captures all the symmetries of the triangle. So this is our first hint that groups are really all about symmetries. So that example of the dihedral group, it really captures the physical importance of the study of groups. So groups describe symmetries in a physical system. Okay, so now for the question we've all been waiting for. When are two groups basically the same? So we're going to proceed in the same direction we did with the sets. So when we studied sets, we preserved the structure of the set by, so if I have two sets, A and B, we preserve the structure of a set by mapping A to B, right? So I take a map F, I can get from A to B, and well, A is a set, B is a set, and so a map is the thing that preserves the structure of a set. Okay, so if I want to preserve the structure in such a way that they're equivalent, then what I use is a bijection. So the equivalence between two sets is captured by a bijection. Okay, so strictly speaking, a map preserves set structures. The bijection does a little more by requiring that the sets are the same in some sets. So the first thing we want is a way to get from one group to another, and a map will only take us from a group to a set. So we are in just a little bit of trouble. Right? So we can get from a group G to another set H with a map. So let's call it phi. How do we make sure that the set on the other end is also a group? Well, if G is equipped with an operation, so let's call the operation star G, and H has an operation star H, we want to make sure that H is closed under this operation. So what we do is we require that phi G1 star G2 is equal to phi of G1 star phi G2. So what this does is this translates the binary map structure on G to H and make sure that they're the same. So a map that has this property is called a homomorphism. So if you're a map from G to H and you have this property, then you are a homomorphism. Okay, so a homomorphism accomplishes this task of getting from a group to another group. Now, how do we make sure that the groups are just a relabeling of one another? Well, we saw how to do that with sets, right? We need this homomorphism to also be a bijection. Then it preserves the binary map structure, but also the set structure. And that's the only structure a group has. So here's a definition. And isomorphism, I'll reuse that word. This time it's an isomorphism of groups, is a bijective homomorphism. So again, homomorphism preserves the structure of that binary map. And an isomorphism, it seals the deal by making sure that that underlying set, those underlying sets are equivalent to each other. So the bijective property tells us they're isomorphic as sets, and then adding the homomorphism property tells us they're isomorphic as groups. Okay. So where we go from here, we have a notion of equivalence between groups now, and now we should talk a little bit about the classification. So we saw last time that the classification of finite sets, not infinite sets, but finite sets, was really easy. All we had to do was count the number of elements in each set to determine if they were isomorphic. So unfortunately, or maybe fortunately, depending on the way you look at it, the same cannot be said for finite groups. So here's an example indicating that. So if you take two groups, here's one called Z4, and here's another one called Z2 cross Z2. So this guy is the set of integers 0, 1, 2, 3, with the understanding that when you add two of these, you do it modulo 4. So what does that mean? That means I subtract 4s until I get something less than 4. So for example, 2 plus 3 modulo 4, or mod 4, is equal to 5 mod 4. And now I subtract 4s until I get something less than 4. I subtract 4 and I get 1. That's the way our modular arithmetic works. Now, I have two copies of Z2 here. This is all the pairs of elements N, M, such that N and M are in Z2. Or if you like, it's sufficiently small that I can just list out all the elements for you. So we have 0, 0, 0, 1, 1, 0, and 1, 1. And the operation here works works as follows. So if we have NM and we want to add N prime, M prime to it, we do it component wise. Right? We do N plus N prime and M plus M prime. Okay, so these two things are both groups. I won't prove it to you, but the point is that these have the same number of elements. So this one has 4 elements, and this one also has 4 elements. Okay? But in fact, these are not the same. So these are not the same group. They're not isomorphic to each other. Okay, so that's just an example where this fails. An easy way to prove that these things are not in fact isomorphic to each other is to show that the order of an element, which is the number of times that you have to add it to itself before it reaches the identity, this is preserved under an isomorphism, right? And then you would just look at the orders of all the elements, right? Order of the identity is 1, because I just added 0 times to itself. Order of 0, 1 is 2, because 0, 1 plus 0, 1 is 0, 0. Same thing for this guy. It's order 2, it's order 1, 2, 2. This is also order 2. Then I go over here and I say, okay, this guy's order 1. This is order 4. And so immediately there's a difference, right? And these are not the same groups. Okay. But I'm getting ahead of myself. All right, so I don't want to go into too much detail on the actual study of groups. Sorry, was there a question?
Yeah, sorry, I must have misunderstood something. You were saying that individual elements had an order?
Yes, yeah. So the order, maybe I should define this. The order of an element G of a group G is the smallest positive integer, let's call it K, such that G, what's the way to write this with that star notation? Okay, so I think I have to abandon this clunky notation before I can explain this. So I've been writing, for the operation in G, I've been writing G star H, right? I'm going to drop this star from that one, right? And I'm going to call this just GH. So that means that G star G is going to be written G squared. Okay. So the order is the smallest positive integer such that G to the K is equal to the identity. So in our groups here, these groups are additive. Additive groups, you usually do write the plus sign, right? So the order of 1 is 4 because 1 plus 1 plus 1 plus 1 is equal to 4, which is equivalent to 0 modulo 4, right? And that's the identity element. The order of 0, 1 is 2 because 0, 1 plus 0, 1 is 0, 0 because 1 plus 1 is 0 modulo 2, right? And that's our identity element. Okay. So I don't want to go into too much detail on the actual study of groups because we're here to talk about representation theory, not groups themselves. Anyway, I will say that the classification of finite groups is actually really complicated. So what we do is we kind of decompose finite groups into these fragments called simple groups, and we classify those. And we'll see this idea of simplifying the process again when we come to representations, and we split representations into products of irreducible representations, or sorry, direct sums of irreducible representations. But anyway, for groups, we split them into simple groups, and it turns out that I'll just quote the theorem. I can't prove it to you because the first proof of this was given by oh geez, I think I wrote it down. It consists of tens of thousands of pages and several hundred journal articles written by about 100 authors, all published between 1955 and 2004. So I will not prove this to you today, and that's my excuse. Anyway, the theorem is that every finite simple group doesn't really matter what simple means for us. The point is that groups can be decomposed into these things. But every finite simple group is isomorphic to one of the following. There's the cyclic group of prime order. So an example of that is that triangle that I was talking about earlier, like all the rotations, not the flips, that's the dihedral group, just the rotations. There is what's called the alternating group of degree greater than or equal to 5. So the alternating group is a subgroup of what's called the symmetric group. The symmetric group is the group of all permutations of some number of objects. And the alternating group is just the set of all, is it even or odd? I think it's even permutations. Yes, thank you, Roy. And there's also what are called the groups of Lie type. And I don't know anything about these. I assume they're not the same thing as Lie groups, which are in general not finite groups. In fact, I think every finite group is a Lie group. So they're not. Thank you, Marguerite. Okay, and then, so we have these three types of groups, which are infinite in extent, right? There are infinitely many groups that fit these three classifications. And then there's also one of 27 groups called sporadic groups. And there has been some work trying to understand why these 27 groups are different than these three infinite sets or classes of groups. Yeah, but I won't say more than that. It's an interesting topic to look into if you're curious, but I won't say much more. Okay.
Oh, I have a question.
Sure.
Was it called D3, the triangle we went over? Is that a sporadic group?
It's D6.
D6, sorry.
I don't know exactly what these 27 sporadic groups are. I know the monster group fits there, which is a very large order group. But I don't know much more about these than that. D6 is isomorphic to anything that I can give you a concrete answer on. Yeah, I'm not sure off the top of my head. I imagine it's not, but D6 is not simple. I cannot remember. We could work it out, but I don't want to do that right now. Okay. So, well, actually, yeah, no, I don't know. Okay, so the representation theory of finite groups, what we're here to discuss, right? What is it? Well, it's both an attempt by algebraists to extract information from a group in order to study the group itself. Right? And it's also just an interesting theory in its own right with applications in theoretical physics, among probably some other fields, but I'm mostly interested in the theoretical physics part. So there are a few useful constructions that I want to end on from group theory that will help us moving forward. So how am I doing on time? Okay. All right. So we can go into a little detail on these. So first, well, I haven't mentioned what a subgroup is. A subgroup, let's just start with that. Is a subset. So a subgroup H is a subset of another group G, which is closed under the binary map of G. So H, if it's a subset of the group G, and it's also closed under that map, that means that if we take two elements of H and we multiply them or apply this binary map to them, then the answer is still in H, right? So if H1 and H2 are in H, which is a subset of G, then since it's a subset of G, we can apply this binary map from G, right? So that's H1. I'll write the star here again so we understand. And this thing is also inside of H. Okay. Or in the notation that I'm trying to switch to, that means that H1 times H2 is still in H. Ooh, not running out of ink. All right. So if you have this property, you're called a subgroup. So the idea is that you're just a group in your own right, but you live inside of another group. Okay. So Vincent, you want me to repeat last part about a theory of group representation? Yeah. Okay. So what I was saying earlier was representation theory of finite groups is it's an attempt by algebraists to extract information about the group itself that the representation is associated with. But on the other hand, it's also just an interesting theory in its own right with applications in theoretical physics. So groups describe symmetries in a physical setting, and representations are a means to study that. Okay, so back to the extra bits. So there are special subgroups which are called normal. So a subgroup N and G is called normal when G and G inverse sits inside of N for all G and G and N and N. And in this case, we write, this is a pretty common notation, this symbol, which means that N is a normal subgroup of G. Okay. So this operation here is called conjugation. So N is being conjugated by G. And what this says is that a subgroup which is closed under conjugation is called normal. So notice that this is not the same thing as the stronger condition that G and G inverse is equal to N, because this is just commutativity. So a group that is commutative is normal, or a subgroup that's commutative is, well, that's not quite right either, because we're conjugating by elements of G. Yeah. But if G is commutative, well, N is a subgroup of G, and so this will be a normal subgroup. Okay, so if you have this property of being closed under conjugation, then you're normal. Okay, so why do I mention this? Because there's another useful construction. Normal subgroups allow us to construct what are called quotient groups. So quotient groups are denoted G mod n. So n is a normal subgroup of G here. So our assumption is that n is normal in G. And this is, as a set, it's the set of all cosets of n. All left cosets. A coset is just a multiple of the set n by some element of G. And it turns out that this thing has a group structure whenever the subgroup here is normal. And so actually, I think this is an if and only if statement. I think that this structure with the operation Gn times Hn is equal to G times Hn. So this is our operation. I think this is a group if and only if this the subgroup is normal. Okay. Anyway, there's another way to think about quotient groups using equivalence relations. I think that maybe it's not worth getting into. If we come across this notion again in the future, then we'll discuss it. But for now, let me just give you the last useful thing here. If I have two groups, I can get a bigger group by taking what's called the direct product. It's G cross H, which is the set of all pairs, remember, where G is an element of G and H is an element of H. And the operation is just component-wise. So if I have G1, H1, and I want to multiply it by G2, H2, that's the same thing as G1, G2, H1, H2. That's how we define it. And this thing is a group. And it follows from the fact that G and H are both groups. Okay. So if we need anything else along the way, when we study representations, then we'll discuss it then. So next week I will talk about we'll actually get into Steinberg for the first time. So we're going to do chapter 2 of Steinberg next week, which is just a review of linear algebra. And from there, the following week we'll start chapter 3, which is the actual basics of representation theory. So, any questions?
I have a naive question. So when you go back to the theorem where it's talking about every finite simple group is isomorphic, would
Yes.
a sufficiently large simple group be isomorphic to every cyclic group that's like under it? Like so if you had something that was like 6, would it be of the primes under it, or would it just be the lowest order one?
I don't think I understand. Hang on. So if I have a group and its order is sufficiently large, and your example is 6, order 6.
Sure. Yeah. Would
Okay.
that be the cyclic groups of prime order, like 3, 2,
Well,
and
no.
1?
No,
Or-
I mean, if it's built out of cyclic groups, then yeah, it'll be the one smaller. But chances are it's not. I think if you are in abelian group, so that's the one that commutes, right?
Right.
So G times H is the same thing as H times G, then I believe you are built out of cyclic groups of prime order. But if it's not abelian, then it could easily be one of these other things.
Wait, so if it is abelian, which cyclic group would it be isomorphic to? In like
It would be isomorphic to a product of cyclic groups. Right, so not one cyclic group in particular, but a product.
so
of.
it's allowed to be. Sorry, is that part of the theorem, and I just don't see it.
Maybe
Okay.
maybe it'd
'Cause
be
it says
helpful to talk
one
about what
of the
simple
five.
is.
Yeah, sorry. I should clarify. When I said it's being built out of simple groups, I meant like sorry, products of simple groups. I meant a group in general is built out of product of simple groups. And if you have a simple group of order 6, well, it may or may not exist. If it is a simple group of order 6, it's not going to be a cyclic group because the cyclic groups have that are simple have prime order. Okay. Sorry, and when I was considering the example earlier, I was considering just a group of order 6, not a simple group. Okay. I don't know enough about this topic to tell you exactly which group it would be if it exists. Okay. But a simple group is just a group that has no non-trivial normal subgroups. Right. So the only normal subgroups are the trivial group, which is just the identity by itself, and the group itself. So a group is always normal in itself, and the identity is always normal in a group. Right? If there are no other normal subgroups, then it's called simple. Any other questions? All right, so let's stop this recording.